All right, so let's talk about fission and fusion. What are these things? They vary by one vowel and one consonant. Well, fission is when you have a large nucleus that splits into two smaller nuclei. And fusion is basically when you take a couple of small nuclei and whirl them around and smash them together and create a big nucleus. So one is breaking down, the other one is building up. So both fusion and fission release enormous amounts of energy. And I think fusion, it says here, releases more energy per gram than fission does. And you're going to have one of those equations like we've seen with decay, where you're not going to be able to balance it based upon the elements that are going into the reaction and coming out of the reaction. You have to use the mass number and the proton numbers to make sure you're balancing your equation. So here what we see happening is that we have uranium, here's our uranium, and we have an incoming neutron headed right for that uranium, and then there's a big bang right here. And what we end up creating is, oh look, some barium and some krypton, and then we create three more neutrons that and also release some energy. I believe it's gamma rays that get released here in this reaction. So this is an example of fission, because we've taken a large nucleus, which is uranium, and split it into two smaller ones, krypton and barium. Now, often when you have fission, you're going to have what's called a chain reaction, which means that you create something that is going to create the reaction again. So here we have this, let's say it's uranium, and we have an incoming neutron, and it's going to cause, so yeah, we got uranium, and this neutron's coming in, and it's going to cause uranium to split into the two smaller particles, which are barium and krypton, and it's also going to release some other neutrons in the process. And these, one of these neutrons here is going to find another uranium. That's what we see happening right here. A couple of these are just going to kind of be released out into the universe. And then in the case of krypton, for example, this is just an example, it is possible that the neutron that was released by this uranium just passes through this krypton, and that it's going to instead find another uranium, and then we're going to have another set of reactions occurring, so that we have this uranium that absorbed just this random neutron is going to create more barium, more krypton, and a couple of more free-floating neutrons looking for somebody to whack. And then because this neutron passed through krypton, it's going to find a uranium, and it will split it into another barium and krypton and create a couple more neutrons that are looking for somebody to smash into. And it gets triggered again. So in this instance, we see now barium having the pass-through neutron that will then find a uranium, and then this neutron from this uranium finds another one, and this one finds another one, and this one finds another uranium, and we have another set of reactions. All these possibilities are represented here. So this is an example of a chain reaction, a fission chain reaction. So in the fission process, it's the neutrons that are the driving force. So you only need a small amount of neutrons to start the chain reaction occurring, and that's what we just saw on with the example of the neutron coming in and impacting a uranium atom. Now, many of the neutrons produced in fission are either ejected from uranium before they hit another uranium, or they get absorbed by surrounding uranium. And the minimum amount of fission isotope needed to sustain a chain reaction is called the critical mass. So there's this threshold amount that you have to have in order to create that chain reaction. If you don't have enough, then it's possible that some of those neutrons that you're trying to utilize to create the chain reaction get absorbed, and nothing further happens as a result. Now, there's only a few fusionable isotopes, and they include uranium-235, plutonium-239, and plutonium-240. So uranium comes in with 92. I want to say 92 protons. I'm doing that from memory. And plutonium is just a couple of doors down. I think they have 94. So we're talking about, some pretty big atoms at this point. Now, natural uranium is less than 1% of the fissionable isotope, which which means that the rest of what we're seeing with naturally occurring uranium is uranium-238. And that means that there's not enough naturally occurring uranium-235 to sustain a reaction. So what do? Well, we enrich. We enrich the supply, which means that we have to create uranium-235 in order to get the reactions that we're looking for. Now, about 90% of the fissionable uranium is going to be weapons grade, and only about 3% is going to be reactor grade. This is why when our government or any agents of our government choose to sell our fissionable isotopes to people who are not necessarily our friends, that it can be a problem. Chances are they are not using it to supply power to their population. They're using it to create weapons that could likely be used against us. Just saying. So that 3% of uranium-235 is used by nuclear reactors to generate electricity, and about 20% of all U.S. electricity is generated in this way. Now, like I said, the reactors are using uranium-235, and the way that this works is that they're using the uranium to produce heat. The heat in turn boils water, which then turns to steam, and then steam is used to turn a turbine, which generates the electricity. Now you could use coal to do the same thing, but when you compare the nuclear fission with burning coal, you can see that there are some advantages. If we look right here, it takes about 50 kilograms of fuel to generate enough electricity to supply 1 million people. If we're talking coal, it's about 2 million kilograms. So you can see there's a big difference in how much fuel it takes to actually generate that power. The other thing is that when you burn coal, you create nitrogen dioxide and some sulfites that can both add to acid rain. It also produces carbon dioxide, which is that greenhouse gas. And that is considered to have harmful effect as well. But if we look at nuclear power plants, in the act of making electricity, they don't do any significant pollution. There are problems. We'll look at that in just a second. But when you look at it on this slide, it looks like the clear choice is nuclear power. So in order for us to understand possibly some of the drawbacks of nuclear reactors, we need to understand a little bit more about how they work, and what is at the heart of the functioning, the core, which is what we're going to be looking at. So the fissionable material, the radioactive material, is stored in these long tubes called fuel rods, and they're arranged in a particular way. And between the fuel rods are the control rods that are made of neutron absorbing material, such as boron or cadmium. And these are needed in order to help sustain the chain reaction that is being relied upon to drive the whole power plant. Now the rods are placed in a material called a moderator to slow down the ejected neutrons, and this allows the chain reaction to occur below critical mass. So they're basically manipulating the circumstances at which they can create this chain reaction. So as you see here, already just on this one slide we can see that there are several checks put in place in order to put a brake on this very volatile reaction that can happen, because if it goes out of control, it can be a big problem. So yes, there are concerns about power plants. One of them is core meltdown. So what happens here is that water gets lost from the core, because remember you're boiling water and having to generate the steam in order to turn the turbine. And when that happens, the core melts down. And we've seen this happen in at least in my lifetime, I was alive when Chernobyl happened, and I think probably most of you were alive when Fukushima happened, because that was not too long ago. And it's a mess. Those communities don't recover very quickly when that happens, because and not only do the people die from the radiation, but then all the everything around that area is now contaminated with radiation, and you have to wait for a lot of years for those radiation levels to die and return to something that can allow life to resume there. Also, there's a concern about how do you dispose of the wastes of radioactivity. So, for example, there's questions about how do you reprocess it? Is underground storage safe? And let's see, we have the Federal High-Level Radioactive Facility at Yucca Mountain in Nevada. Now, we've had some of these leak, which has been a problem, because then you end up with contaminating water supplies and all kinds of fun stuff like that. And then what do you do once you're done with this reactive substance and you have to move it to a place where you're going to store it and hope it doesn't spill out? Well, then you have issues with transporting the waste and the exposure of the population when that's happening. And then you have to deal with the dilapidated, no longer safe or viable nuclear power plants, such as Yankee Row in Massachusetts. So even though, while it's up and functioning and is providing a great deal of power, seemingly effortlessly, the concerns with power plants are long-term, because the half-life of the uranium is long-term, and once that area has been contaminated, you're not going to get back to it for a lot of years. So there are concerns. Nothing comes without a price. So where does the energy from fission come from? Well, during nuclear fission, some of the mass of the nucleus gets converted to energy, and that's complements of Einstein's E equals mc squared. You might remember that the mass of a particle accelerated to twice the speed of light will convert into energy, and that's what we see happening in fission reactions. So for each mole of uranium-235, it produces about 1.7 times 10 to the 13 joules of energy. That's not heat, that's energy. Even the most exothermic reaction that we could come up with produces only about half of what's being produced by a mole of uranium-235 undergoing fission. So you can see what the lure is about using this as an energy source. Now, as we just saw, we understand that when a nucleus undergoes fission, when it gets divided into smaller parts, we're going to lose some of the mass, because some of those particles, or some of that will get converted into energy. That's the E equals mc squared. Now, interestingly enough, when a nucleus forms from separate protons and neutrons, it also loses a little bit of mass. And this is called mass defect. So what's happening is that in order for the particles to come together, some of the nucleons are, some of the mass of the nucleons gets converted into energy. And the difference between the mass of the separate protons and neutrons and the combined protons and neutrons that are now making up a nucleus, this is called the mass defect. Now, if we think about this as independent particles, they are high energy, but when they come together as a collective, now they're lower energy. And this is what Mother Nature favors. She likes to create low energy states from high energy states. So this makes sense to us now why this is even happening. The energy that is released when the nucleus forms is called combining energy. So as all these little particles combine, the energy they release gets called binding energy. Hope that makes sense. And here are your here are your numbers. So 1 atomic unit of mass defect has a value that can be assigned to it. And the greater the binding energy per nucleon, the more stable that nucleus is going to be. Okay, so let's talk a little bit about how we could do some calculations involving our mass defect and binding energy. So we know that mass defect is a difference in mass from independent nucleons then becoming a nucleus, and that information is most likely going to be given to you as we see here in the chart. So as individual single nucleons, the mass of our element is given right here, and we're told that once they enter into a union that the mass has been reduced to this. So in order to find the mass defect, all we really need to do is take the difference between the two masses, the beginning mass and the ending mass, and then that will give us the mass defect amount. Now we'll notice that this is in atomic mass units. And when we need to convert this mass from atomic mass units into kilograms or grams so that we can ultimately drop it into our equation to calculate binding energy. And so we're going to use a conversion factor that tells us that one atomic mass unit is equal to 1.66054 times 10 to the negative 27th kilograms. So this is our conversion factor that we use. Now at this point all we really need to do is, in order to find our mass, we're going to take our value that we calculated from mass defect and multiply it by our conversion factor. That will get us out of atomic mass units and into kilograms, and we have a new value. So this is our M for our equation, E equals mc squared. So that's what's next. So in order to find the binding energy, or the energy that was created by this mass, this amount of mass being converted into energy, we're going to use E equals mc squared. So we plug in our numbers. We're going to take the mass from our mass defect that we converted into kilograms, and we'll drop that into the equation. And here's twice the speed of light, and we do the math that's involved, and we can see that our binding energy is equal to 2.7593 times 10 to the negative 11th joules. So the math isn't really hard. It's just understanding what formulas that you use, and making sure that you understand the definitions of what mass defect is and what binding energy is. So up to this point, we've been talking about fission, which is taking large nuclei and dividing them into smaller ones. Now we're going to be talking about fusion, which is when we're going to be taking small particles and bringing them together to create a bigger one, a bigger nuclei. So let's see what's happening here. So the sun uses fusion. It uses the fusion of hydrogen isotopes to make helium, and this is a power source that drives the sun's activities. Now it requires a high input of energy to initiate the process, but it produces 10 times more energy per gram as fission does. So it's a pretty high-powered thing. And the other beautiful thing about this is that it produces no radioactive byproducts. Unfortunately for us, the only way we know how to use it is in the H-bomb. Now, through a large part of this chapter, we've been talking about fission. And fission is when you take a large nucleus of uranium, for example, and then you hit it with a neutron, and then it blasts into two smaller particles, one of which is, I think, barium, and the other one is krypton. And to us, that seems second nature. But there was a point when the science community didn't understand what was happening. They didn't understand that during radioactive process, atoms of one element were changing into atoms of another element. But Rutherford was the first one to lead the charge on this, and he termed this conversion as transmutation. And So basically, for one element to change into another, we know that we have to have that change in the number of protons. We see that with fission, where we go from a large nucleus to a to a couple of smaller nuclei particles. That's transmutation. And we also see it with fusion, when we take a couple of small particles, like a hydrogen ion, and we bombard it into, we bombard that with or onto another element and create something new, where we've basically added protons to something and created a different atom. So both of those are examples of transmutation. Fission and fusion are examples of transmutation. Now, we've captured the ability to do artificial transmutation, where we would take high energy particles and smash them into some sort of a target nuclei in order to create a new nuclei. That's the way a lot of our new discoveries, quote, of elements have been have come about, is that we created them in the lab. They're not stable, but we've got them for just a brief second. The particles may be radiation from another nuclide or changed particles that are accelerated. And Rutherford was playing with some of this. He was able to make oxygen-17 by bombarding nitrogen-14 with alpha rays from radium. So they were messing around with this at the turn of the century, doing some crazy stuff. So yeah, we can do that. We can create these new particles, but their stability can often be questionable. And how long they stick around, yeah, that's what you see at the higher numbered particles in the periodic table. Sometimes periodic tables will leave those spaces blank, or they'll designate them with like an O symbol, because they exist for a moment in these artificial transmutation settings. So in addition to bombarding a nucleus with another one, such as taking a hydrogen ion and bombarding a different nucleus with it, a different element with it to create something different, you can also bombard them with neutrons. Now there's a couple of mechanisms that we use, a couple of different ways that we do this artificially. One is to use a linear accelerator, and the other one is to use a cyclotron. Now, studying the effects of radiation is important because it can affect our biological tissues, so it can affect our bodies, and it can also affect other biological tissues, such as insects and plants. And understanding those effects help us to either manage negative exposure or to create ways that allow for the enhancement of our lives. So we might remember that radiation is high energy, and it's high energy enough to knock electrons from molecules and break molecule bonds. This is the ionizing radiation that we're talking about. And in fact, this energy is so powerful it can damage biological molecules by knocking our electrons around and breaking up bonds. That's one of the problems when it messes with your DNA. If you have ionizing radiation hitting your DNA, it can mess up your DNA sequence and cause some problems when you go to reproduce. Acute radiation damage, this is what happens when you have high levels of radiation exposure over a short time, and it can kill a large number of cells. This is what we saw happening with the people that lived near Chernobyl, and this has also happened to the workers who went in immediately after that in order to do the cleanup. They got exposure to high levels of radiation, and it killed a large number of cells, and it killed a large number of people as a result of that. What happens with acute radiation is that it causes a weakening of the immune system, and it lowers the ability of your body to absorb nutrients because things just stop working as they should, typically because of cellular damage. So when you weaken the immune system, then that means that you're no longer able to fend off very opportunistic, easy to kill bacteria and invaders, and now you're susceptible to things that that you should be able to fight off. That's one of the problems. The other thing that happens is that if you don't have the ability to rebuild your tissue because you don't have appropriate nutrients coming into the body, then that's another problem. So those are two big problems that happen when you have acute radiation damage. And that's hard to recover from because your body won't last long without proper nutrition in order to drive cellular activity. So what about low doses of radiation? Well, low doses of radiation over a time period show an increased risk for developing cancer. And that's because it damages the DNA. And even though the body's really good about repairing damaged DNA, it might not be able to overcome the effects of the ionizing radiation. Also, low doses over time can damage the reproductive organs, which can lead to sterilization, or it can lead to genetic defects in offspring. So this is what we see happening in the survivors of Chernobyl. Even though that happened, gosh, a long time ago, the children that were exposed and were able to recover from the effects of the radiation exposure are now giving birth to children that are suffering genetic defects because the long-term effects for those people who were exposed is that it damaged their reproductive organs and their sperm and their eggs. Now, there's a number of ways that we can measure radiation exposure. One of them is the Curie, and it's the exposure of 3.7 times 10 to the 10th events per second, regardless of the type of radiation it is. And then we have the Gray, and I believe the Gray is the unit most often used to measure exposure, like in a nuclear power plant. And this is the amount given per kilogram of body weight. And then we also have the rad. The rad is dependent upon the Gray, though. We'll see that there's that relationship. And then we also have something known as the REM. And the REM takes into account other factors that can go into exposure of radiation that might not be accounted for by the Gray or the Curie or the rad. Actually, the rad is part of the REM. So when we think about the effects of radiation on biological tissues, there are factors that help us determine what these effects might be and to make some predictions. One of the factors is the energy of the radiation. The more energetic the radiation, the larger the effect it'll have on biological tissues. The other is the penetrating ability of the radiation. So gamma has the greatest ability to penetrate alpha, because remember alpha is those big clunky hydrogen nuclei particles. So yeah, how far into the body it can go kind of predicts where the damage might actually end up. Ionizing ability of the radiation, how likely is it to knock out an electron or break a bond? Well, the alpha has the greatest effect, gamma has the least effect, but again, looking at these can help us predict what's going to happen. The chemical characteristics of the radiation also come into play, which means that we're looking at the half-life of the radionuclide, the biological half-life of the element itself, the physical state of the radioactive material, and whether or not the radionuclide participates in any sort of chemical reactions in the body. So these all have to be taken into account when determining the biological effects of radiation. Even though radioisotopes have a detrimental effect on biological tissues, medicine has been able to employ some of them to our benefit. So, for example, nuclear radiation can be used to visualize and test structures of the body in order to determine how well they're working or if they're working or not working. So, for example, you can take an atom and label it. So you're taking an isotope and you're labeling it, and then you're doing a series of imaging and following it as it moves through the body or through an organ system or through an organ or some tissue in order to see what's happening there. So that's an example of that. Nuclear radiation can also be used to treat diseases. because the radiation can allow for the attack of unhealthy tissue while not necessarily harming the healthy tissue around it. So we know that certain organs and certain tissues have a particular predilection towards certain elements, and we can use this information to create something known as radio tracers that are basically a tagged isotope. And using these tagged isotopes with imaging, we can follow this, we can trace the movement of this particular species through the body. So for example, most of us might have an understanding that iodine is something that the thyroid takes up from the blood and uses in order to make thyroid hormones. Well, if the thyroid has grown some lumps, you might be suspicious about what those lumps are. Sometimes it's just an overgrowth of normal tissue. Sometimes it's a tumor. And what you would do is you would give the patient some of these nuclides, some of these iodine tagged nuclides, and you would image the thyroid, and eventually those would make it to the thyroid, where the thyroid would light up like a Christmas tree, provided that it is using that iodide, that tagged iodide, in order to do its business. Now, if you have a part of the thyroid that is no longer thyroid tissue, maybe it's become a tumor of some sort, then that would not be taking up iodide doing thyroid type stuff. It'd be doing other things. So that would be your first indicator that you had some sort of a foreign growth or foreign mass on the thyroid. So that's how these tracers are used. They're looking at the tissue involved, making sure that all the tissue is uptaking the tracer as you would intend for it to, and if it's not, then that gives you cause for maybe to do something more aggressive as far as a diagnostic procedure. PET scans are used to study brain function, and PET stands for positron emission tomography. So this is using a fluorine that's been tagged, and it's an amazing technology because they can do it in real time. So they can actually have you look at a picture of a square and see what part of your brain lights up, or look at a picture of a circle and see if another part of your brain lights up. And in fact, I believe that is what happens. So yeah, positron emission allows us to see what the brain is doing, where the brain is lighting up given certain activities. So we can use radiation as a form of treatment in some disease process, such as cancer. Cancer cells are more sensitive to radiation than the healthy cells that surround it, and so radiation can be used to selectively kill the cancer cells without doing significant damage to healthy tissue. There can be a little bit, but there wouldn't necessarily be a ton of damage to the healthy tissue. So you can use something called brachytherapy, which replaces the radioisotope directly at the site of, that places that radioisotope directly at the site of the cancer. So they can zero in on that tumor and blast it. There's teletherapy, which uses gamma radiation from cobalt to penetrate inside the tissue, if that's where the cancer is somewhere buried in the body. And then there's radiopharmaceutical therapy that uses radioisotopes that concentrate in one area of the body. So these are just some different ways in order to deliver that damaging radioisotope to that cancer cell. Now, in addition to medical uses of radioactive isotopes, there are non-medical uses. For example, in smoke detectors, there is an isotope that is utilized, and when there is smoke in the air or even enough water, such as high humidity, will trigger a smoke detector. That basically means that it breaks the circuit that's going through there, and it sounds the alarm. So yeah, that's an example of it. Insect control, selectively sterilizing the males of an insect species in order to prevent them from taking over and damaging crops. Food preservation, yeah, so there's some talk about radiating food, produce, in order to get it to have a longer shelf life. We're being told, right, as of now, that it's harmless. I'll be interested in what long-term studies reveal with that. You can use something called radioactive tracers to follow atoms throughout certain reactions so we can get a better understanding of our world at the molecular level, as well as using these isotopes in various chemical analysis. And what type of chemical analysis, you say? Well, it can authenticate art by looking at the paint and as well as maybe even ceramics and seeing what's being able to use those isotopes to detect age. Agribusiness will use it to develop disease-resistant crops. Uh, you can use it. It's used in the non-stick coatings for pans. So yeah, there's a variety of ways that radioisotopes are used, and there's plenty listed right here for you to read. And with that, we are done with chapter 17.